The research paper delves into the application of deep reinforcement learning (DRL) for autonomous navigation in unmanned vehicles, with a specific focus on the Deep Deterministic Policy Gradient (DDPG) algorithm for handling high-dimensional continuous action spaces. The model of an Ackermann robot and the structure of the DDPG algorithm are detailed. Experiments in a simulation environment demonstrate the improved algorithm's outperformance over traditional DQN and DDQN algorithms in path planning tasks, contributing significantly to the advancement in autonomous navigation for unmanned vehicles. The proposed Deep Deterministic Policy Gradient (DDPG) algorithm optimizes path planning in autonomous navigation by directly generating usable local trajectories. This leverages the continuous action space of DDPG, enabling the vehicle to avoid obstacles and achieve efficient path planning through end-to-end reinforcement learning. Reinforcement learning is employed as a powerful machine learning paradigm for training agents to make decisions by interacting with an environment. DDPG is an off-policy algorithm designed for environments with high-dimensional continuous action spaces, combining the strengths of Deep Q network, DQN, and policy gradient methods. The mobile robot model used in this paper is based on a four-wheeled vehicle employing an Ackermann steering mechanism, which is widely used in car-like robots and vehicles to achieve efficient turning and maneuverability. The position and orientation of the vehicle can be described by its coordinates in the plane and the orientation angle. The kinematic equations of the vehicle are described by equations 1, which take into account the vehicle's velocity, steering angle, and the distance between the front and rear axles. The DDPG algorithm consists of a policy network and a target network. The policy network outputs a specific action given the state, while the target network is a slowly updated copy of the policy network. The DDPG algorithm uses a deterministic strategy to select actions, and the output is not the probability of the behavior, but the specific behavior. The algorithm has a strong deep neural network fitting and generalization ability, as well as the advantage of processing continuous action space. The DDPG algorithm is applied to the path planning process of the mobile robot, enabling the mobile robot to output more continuous actions and reduce decision errors during movement. The actor current network outputs the action of the mobile robot according to the state and surrounding environment information, and the critic current network outputs the Q value as the evaluation of the action. The target network of the actor and critic is mainly used in the subsequent update process. The structure of the DDPG algorithm is shown in Figure 1. The actor network consists of a policy network that selects actions based on the current state and a target policy network that is a slowly updated copy of the policy network. The policy network outputs a specific action given the state. The critic network evaluates the action taken by the actor by estimating the value of the state-action pair. It includes a target evaluation network, which is also a slowly updated copy, ensuring stability and training. The target networks are updated using soft updates to ensure stability, as described in Equation 2. In a simulation environment, an experiment was conducted to verify the feasibility of an improved algorithm. This algorithm aims to enable a robot to avoid collisions and reach its target point through the shortest path. The training rules include a fixed initial point, a random target point, and a maximum number of steps allowed. The experimental environment and parameters are detailed in Tables 1 and 2, respectively. A comparison with DQN and DDQN is also performed on a comprehensive test problem, involving a rectangular area with houses and trees to test the robot's autonomous exploration. The DDPG algorithm structure is illustrated in Figure 1, highlighting the critic network, policy network, and their respective optimizers. This experiment demonstrates the potential of the improved algorithm in enhancing the robot's navigation capabilities in complex environments. The paper presents a comparative study on training three algorithms DDPG, DDQN, and DQN for path planning in an autonomous navigation system. The results indicate that the DDPG algorithm outperforms the others, achieving the highest success rate in shortest average time per episode. Figure 3 illustrates the training rewards for each algorithm, with DDPG demonstrating superior performance. Table 3 provides detailed performance metrics, showing that DDPG has a success rate of 97%, an average time per episode of 45.3 seconds, and a training time of 16 hours. In contrast, DDQN and DQN algorithms show lower success rates and longer average times per episode, along with varying training times. The study concludes that the DDPG algorithm is the most effective and efficient for autonomous navigation of unmanned vehicles. It significantly improves the real-time planning ability of unmanned vehicles in unfamiliar environments, demonstrating excellent performance in dynamic and complex scenes. This research addresses the challenges of autonomous navigation, providing insights into the potential of reinforcement learning algorithms for enhancing unmanned vehicle navigation capabilities.